Hey guys, welcome back from spring break. I hope you had a relaxing time. I realize many of you probably had to cancel trips and plans, but regardless, we're back and it looks like it's going to be at least May 1st until I get to see your face again. So this is going to be status quo here for the next few weeks. All right, so jump right in. I'm going to kind of split this topic over the course of 2 days. We're going to do some problems in Google Forms tonight, and then I'm going to give you some more problems in Google Forms tomorrow. So just generally speaking, a chemical bond stores energy. Now, a single bond is generally weaker, and double bonds and triple bonds are generally stronger. So it takes more energy to break a triple bond than it does to break a single bond. Okay. Now it also varies between the elements involved, and if you guys look in your textbook, tables 8.4, it will give you like bond energy. So a higher bond energy basically means that that is a stronger bond. Okay, so it not only depends on the elements involved, but also is it a single, a double, or a triple covalent bond. Okay, now, we're going to use this equation a little bit, but for today, I just kind of want to keep things more simple. Just realize when we break a chemical bond, this requires us to put energy in. This would be an endothermic change, a positive change in value, okay? On the other hand, when a new bond is formed, this is going to be an exothermic change. Energy is released, and we're going to get a negative value. Now remember that enthalpy and energy are for the most part interchangeable, so just kind of keep that in mind. Now, you've also got this letter D in there, and that little D, let's not make things too complicated, but this letter D sees that we're always going to look at positive values. Now, realistically, we are going to subtract out the energy of bonds that are formed. So in the end, it's going to represent as a negative value in the long run. So when we're tallying up these values, just be aware that making bonds is exothermic and breaking bonds is endothermic. And when you do the homework, I hope I made that pretty clear so you guys can follow along, okay? All right, so number of moles. If we're just looking at a balanced equation, for the example, we have a balanced equation down here. We can assume, by looking at this equation, that the coefficient is the number of moles. So HH, we can just assume that that represents 1 mole of hydrogen, okay? And if FF has no coefficient in front of it, we can assume that that is 1 mole of diatomic fluorine. Now we do notice that there is a 2 in front of HF. So when 1 mole of hydrogen breaks into atoms and 1 mole of fluorine breaks into atoms, we're actually going to end up with 2 moles of hydrogen fluoride in this case. So just realize that the coefficients from the balanced equation are going to kind of substitute for the number of moles for our first few examples, okay? All right, so guys, I've color-coded some things for you. If you see blue, that represents that energy is being absorbed, that this is an endothermic change. If you see things are red, this represents an exothermic energy is released, okay? So when we start to look at this equation, to break those hydrogen-hydrogen bonds, it takes 432 kilojoules to break the bonds in 1 mole of diatomic hydrogen. And I got that number 432 from table 8.4, okay? When you do the assignment today, I'm going to go ahead and put the values in there, okay? If you want to break all the bonds in 1 mole of fluorine, it's going to take 154 kilojoules to break all the bonds in 1 mole of fluorine. So breaking all the bonds in the hydrogen plus breaking all the bonds in the fluorine adds up to, in this case, looks to be about 586 kilojoules per mole. So this number right here is really just a sum of the 432 times 1 and the 154 times 1. So all in all, to break all those hydrogen bonds and fluorine bonds, it's going to take about 586 kilojoules of investment to do that. Now, on the flip side, when 2 moles of hydrogen fluoride are made, it's going to release 2 moles times the 565. So 2 times 565, 1130 kilojoules of energy is going to be released. So now what we're looking at in the very end is we're looking at all the energy that is taken to break those bonds. Okay, that's going to be a positive 586. And then we're going to subtract out all the energy that gets released when new bonds are formed. So because we're subtracting, that makes it a negative value. So 586 kilojoules to break the bonds, but then we're also getting 1130 kilojoules back when we make new bonds. So when we go ahead and we plug in all the numbers, we actually get a value of negative 544. And that tells me that this reaction is exothermic and pretty much likely to be spontaneous for the most part. Now, things can get a little bit more complicated, okay? All right, so if we look at a molecule of methane, okay, the coefficient from the equation is, well, there's no coefficient, so we can assume that there is 1 mole of methane. Now, that presents a problem because methane actually has 4 bonds. And if we come over here and we look at it, we've got carbon in the middle, and it's surrounded by 4 hydrogens. So knowing the structure of these molecules is very helpful. So we have 1 mole of methane, but we actually have 4 moles of bonds because we have 1, 2, 3, 4 identical carbon hydrogen single bonds. So 1 mole of methane contains 4 moles of bonds, and a single carbon hydrogen bond takes about 413 kilojoules per mole to break. So 4 moles of bonds times 413, we're going to get about 652 kilojoules to break 4 moles of bonds, okay? Now we're going to go ahead and we're going to look at chlorine. Chlorine is a molecule that has a single covalent bond. So if we have 2 moles of chlorine, that's the coefficient 2, 2 moles of chlorine, we're going to look up that value from table 8.4, and it's going to be 239 kilojoules. So 2 moles of chlorine, it's going to take 239 kilojoules to break 1 mole, so we basically double that to get to our 478. Okay, we're going to do the same thing. We're going to do the same thing for fluorine. And if you look at the coefficient, it's going to be 2 moles of fluorine. So we also know that fluorine is a single covalent bond. So 2 moles of fluorine. And if you look in table 8.4, it's 154 kilojoules to break all the moles, all the bonds in 1 mole. So we have 2 moles. Now, what we end up getting is we get all these numbers. And if we add them all together, this is how much energy we need to put in order to break all the bonds on the left side of the arrow. So we have 1 mole of methane, which we know has 4 identical carbon hydrogen bonds. We have 2 moles of chlorine, which has a single covalent bond, and we have 2 moles of fluorine, which has a single covalent bond. So it's going to take us 2,438 kilojoules to break all the bonds on the left side of the arrow. So that's money that we have to invest. We're putting energy in. Now, if we look at the other side of the equation, we're going to make new molecules. All right, now let's go ahead and start with this carbon fluorine chlorine compound. And I think the best thing I can do here is draw it for you. So I know that carbon's going to be in the middle. It's going to have 2 chlorines attached to it and 2 fluorines attached to it. Now the coefficient from the balanced equation, there is no coefficient, okay? So we assume that it's 1 mole. So for every 1 mole of this carbon, chlorine, fluorine compound, we're actually going to get 2 moles of carbon, fluorine bonds. So I kind of represented those in blue. But we're also going to get 2 moles of carbon chlorine bonds. So I'll kind of do these in green. So we looked up our values from table 8.4, and we said for every 1 mole of this carbon, fluorine, chlorine compound, we get 2 moles of single carbon fluorine bonds. So 2 times the 485. And we're also going to get 2 moles of these carbon chlorine bonds. So that's going to be our 2 times our 339. Moving on to the next molecule, which is hydrogen fluoride. Okay, we know that hydrogen fluoride is a single covalent bond, and the coefficient is 2. So I'm going to take 2 moles. I'm going to look up that value. It's 565 kilojoules per mole, so we have to multiply that by 2. And the very last thing that we have to look up is our hydrogen chloride. And we know that hydrogen chloride is a single bond. The coefficient from the balanced equation is 2. So 2 times the energy of a a hydrogen chlorine bond is about 427 kilojoules per mole, so we have to multiply that by 2. Now, if we sum up all these values, this is how much energy is released, okay? So everything in blue, this is the energy that it's taking to break all these bonds. But when we make new bonds on the right side of the arrow, we're releasing energy. So this is a total amount of energy that's being absorbed by breaking bonds. This is the total amount of energy that's released when new bonds are formed. And if we sum everything up, we get a negative 1194 kilojoules per mole. So assuming that this reaction represents really just the number of moles represented by the coefficients, for every 1 mole of reactants, in the case 1 mole of the methane, 2 moles of chlorine, and 2 moles of fluorine, in order to make the products on the right, this is how much energy is going to be absorbed or released. So in this case, a negative value means that this reaction is exothermic, and a negative value means that this likely is going to be a spontaneous reaction. All right, so guys, in your homework for today, a tip is, just make sure you know what the structures look like. I think you're going to have to do methane, I think you're going to have to do ammonia at some point. So if you know the structure, you know the nature of the bond. So ammonia has nitrogen with 3 single bonds to hydrogen. Remember, guys, if you have any questions, you can leave a comment in Google Classroom. Don't be afraid to make that public, or you can email me directly. All right, guys, I'm going to give you the second part of this lesson on Wednesday. So, hopefully we're going to get this over a course of 2 days. I'll give you a couple problems tonight, and then a couple more problems tomorrow. Miss you guys. I love you guys. I'll see you soon.